we want to look at next is that something happens to the system. So when we were looking at these energy transformations, we were talking about, well, a substance went from this to that, and what was happening. So now what we want to do is we have a word for that, and we call it processes. So a process is a change of system state. So I have to have a, I'm going to talk about, so a process is a change of system state. So it describes how the system goes from state 1 to state 2. And if I look at this on a PV diagram, so I have a pressure volume diagram. So I have a pressure volume diagram, and the system, here is state 1, and here is state 2. How does the system change when it goes? So how does the system change when it goes from state 1 to state 2? I could have it go many, many different ways. So I could have it go many, many different ways. If I draw a path, so if I describe a certain way it goes, so this way is a path. So this is a path. And if I draw a solid line, it's indicating that it's an equilibrium path. So the solid line denotes an equilibrium path. So when I look at this line, it means that it varies continuously. So from a calculus perspective, it's a continuous function. So I have a continuous variation, so I have the pressure defined at all times as the system moves from state 1 to state 2. So that means the pressure throughout the system is the same, just as the temperature was in the pool, now we're having the pressure be that way. And so this is an equilibrium path, and now we have, I can put in a dotted line, which means I don't know how it got there. So it was at state 1, it got to state 2, how did it get there? A miracle. No, it was just a non-equilibrium path. And so we don't know what that is. Here we have a continuous path, so it's a differential. And so when I have this means that I can use, it's a continuous function. I'll write it down. And so we have, the system is changing from state 1 to state 2. We see how it goes. Either we don't know what's happening, we just know the final 2 states, or we know what's happening and we have a path. If it's a path, I can use my calculus because I have a continuous function, and I can use differential calculus to describe it. So now we have something if I have more than one process. So what if I have a process and it goes back, and goes back to where it came from. So we have something that's called a cycle, which is 2 or more processes where the initial and final state are the same. So in this case, I take this, I have PV, and so I'm going from state 1 to state 2, along path A. So now, that's the process from 1 to 2 along A. I could go back along B, and there's another path. So now a cycle is 2 or more. You know, or I could have 3 paths, or I could have 5 paths, whatever number of paths I want to have. So I could have 1 to 2, 2 to 3, 3 to 1. So I could have something like that. They're all cycles. So, and they're systems that undergo cycles have certain energy properties associated with them that are very good. So now let's look at a real world example, and let's look at a refrigerator. So we'll have a real world example. And not all of you know how refrigerators work, but let me make a drawing of one, a schematic drawing, and we'll show what's going on so you can see. So we're going to have a condenser. So here's the condenser. It's going to go through a valve. It's going to go down to the evaporator. The compressor back here. And so this is an evaporator. Which has low T&P. So that's this. We have a condenser. And here you're going to have high T&P. Here's your compressor. So you have electrical work going in. And here's your a valve. And the purpose of the valve is to reduce the pressure and lower the temperature. And so what you've noticed, so what you did pay attention to, is that if I have a can of soda, because I know that's the only type of canned beverage that you would drink. So we have a can of soda that you put in the refrigerator. What happens? It's warm, so the T here, T of the soda, is greater than T evap. And so heat's going to flow from the soda into the evaporator, and it's going to, anyway, so what's happening is you have energy leaving the soda going into the evaporator. And that's how cooling occurs in the refrigerator. Then you have a compressor which increases its temperature and pressure of the refrigerant, and then you have a condenser. So typically at the top or behind a refrigerator there'll be coils that are hot, and those coils use room air. There may be a fan, there may not be a fan, that blows over these coils, and this is where you have high temperature and pressure inside. And then it gets cooled down to some approaching room temperature, and then it goes through a valve which drops the temperature and pressure, so now it could be at 30 degrees Fahrenheit, or in the freezer at 0 degrees Fahrenheit, something like that. So this operates on a cycle. So when I look at this, and now I'll make a simplified drawing of this so we can see how this is a cycle. So I have the condenser, I have the evaporator, I have the throttling valve, you're going to have the compressor. And so when I look at this is a closed system. So a cycle works on a closed system. So the mass for a closed system is constant. So the mass within here is constant. It circulates around. So if I just looked at the condenser, it would be an open system because I have refrigerant coming in as a gas and leaving as a liquid. And so that's an open system, but this closed system is made up of open system components. The mass stays constant. So this is a real world example of what a cycle is. And what happens is we can measure properties around the cycle. So we'll measure properties around the cycle. And with this, we can determine the substance's state as it goes through there. And from this, once we know the state, we can determine the energy transformations. And then from this, we get the energy description and transformation. So what we want to look at, next are unit systems, and then we're going to get into properties. So I want to into actual properties like pressure and specific volume, density, and temperature. And what we'll use in this course is the SI system, so we'll be using a consistent metric system as opposed to the English system. But let's talk about unit systems just briefly, and we'll see what they are. And in the text, it talks about the English system in depth as well as the SI system. But I found that in the beginning course, if I have both systems going on, there's confusion based on systems and not on thermodynamic concepts. So I want to keep the system thing as simple as possible so that we can focus on concepts and conceptual understanding. So if I'm measuring temperature, so I could measure temperature in degrees Celsius, degrees Fahrenheit. So I could be doing something like that. Except what we want to do is we'll pick Celsius, and we know that degrees Kelvin is equal to degrees Celsius, but it's 273.15. Normally what we do is we just use 273, and we're using the SI system, System International, so we have mass in kilograms, time in seconds, distance in meters. And obviously we could have derivative units from these, of course. And then I can look at Newton's law, F equals ma. We all remember F equals ma. And what we have is that 1 Newton force is equal to 1 kilogram mass accelerated 1 meter per second squared. So we have that 1 Newton is equal to 1 kilogram meter per second squared. And so we have that definition, and we will come back to use this in what it is. So the Newton, a measured force, and we're interested in force, and so it derives from this in the SI system. Force is 1 Newton. You know that gravitational acceleration is 9.8, so G is 9.8 meters per second squared. So if I had 1 kilogram acted upon by gravity, the force exerted, so if this weighed 1 kilogram, if this had a mass of 1 kilogram, acted upon by gravity, the force it exerts on the, in this case on the tray here, is 9.8 meters per second squared. Now, let's look at some other properties that we'll want to describe. So one of them is specific volume. And I use a script V for that. And so we're going to be talking about that. And so this V is equal to volume divided by mass. Now, I'll tell you that we need to pay attention in your notes as to how you make your V's, because I have volume, which is a big V, I have specific volume, which is an italic or script V, and I have velocity, which is a lowercase v. So sometimes I have all these things going around in equations together. So you have, and if I have voltage, we're up the creek, because then we have a V that I have to put little curly Q's on so I can show that it's voltage. So now what we want to do is, we have this in a large case, but how small can we go? So what happens is, in the text you'll see that there's a development for the limits of macroscopic thermodynamics, and it relates to volume. So we're going to have that this is del V over del M. And this establishes the size of thermodynamics, how large it is. So this del V, and actually it'll be a del V prime, is going to be establish limits of macrothermal. And so if I look at this and I have a little volume, then it would call this del V prime. So if I call this volume del V prime, and it will have a length del A, might have called it del A prime. And so I can characterize this del V prime. So this del V prime is as small as you can go and still see air is air and not as nitrogen and oxygen together. And so if I'm measuring air, for instance, I want to know the specific volume, how small can I go and still have air? And the answer is, that's what this limit is, and it's about 10 mean free paths between collisions. Not that that matters, but if I look at the bouncing of molecules, and you look at, I have a molecule here, and a molecule here, and they have this, and if I look at 10 of these, this distance of 10 mean free paths is about what this is. Does it matter in terms of our lives in this class in thermodynamics? Not at all. So it doesn't matter at all. But we will see that this is going to come into play for our measuring pressure that we'll discuss shortly. And now let's look at problem 2.5 on page 41. You may want to stop the video at this point if you're watching it, so you can turn to page 41, look at problem 2.5, and see what's going on. So that would be a wise thing to do. We'll see whether it happens or not. So now, what we're going to do, if I take this problem, so it was a tank, it was 3 meters on the side, 3 meters, 3 meters, and 3 meters. And it was empty, and it was being filled. So I'm filling it with 300 liters per minute. And the density, rho is density. I might point out that density of kilograms per cubic meter and specific volume of cubic meters per kilogram are the inverse of each other. So I have that rho is equal to 1 over v. So I have, because very often in physics, you've talked about density. Here we tend to talk more about specific volume, but you have to be conversant with both. And so we're talking, in this case, we have the density is 1.2 times rho H2O, the density of water. We have this fluid going in and filling up the tank. It's going in at 300 liters per minute. How long is it going to take to fill up the tank? And what is the mass flow? So there are two questions. So converting from volume flow to mass flow. So liters, a liter is a volume. So that 1,000 liters is equal to 1 cubic meter. So this is a useful thing to know. And you can look it up all the time, but if you have to look it up 20 times, you may learn it. And so if you know this, it becomes handy because a lot of times volumes are measured in liters and not cubic meters. And so what I have then, and I know that the density of water is 1,000 kilograms per cubic meter. So the density of the fluid is equal to 1.2 times that, is equal to 1,200 kilograms per cubic meter. And the volume flow, so I have here volume flow times density is going to be equal to mass flow. So notice that we use the dot over the symbol. The dot over volume means per unit time, per unit time. So if I look at this as cubic meters per second, and this is kilograms per cubic meter, I will end up with kilograms per second. So if I substitute in, and I have 0.3 divided by 60 seconds per minute, times the density of 1,200 is going to be equal to 6 kilograms per second. So that gives me the mass flow. So the purpose of this problem is to convert volume flow to mass flow. And if I had to, I could convert it back the other way. And then looking at how much time this takes. Well, I won't erase this. So the total volume, V is equal to 3 cubed, is equal to 27 cubic meters. And the volume flow rate, so V dot is this, but it's 0.3 cubic meters per minute. So if I divide the volume by the volume flow rate, I'll get time. So T is equal to the volume divided by the volume flow rate. So I'd have 27 cubic meters divided by 0.3 cubic meters per second. And that's going to give me T is equal to 90 minutes. So I know it'll take 90 minutes to fill it up. I know what the mass flow rate is, and that was the purpose of this problem. Now let's look at another property of pressure. And pressure is the intensive property related to volume. So we can see that there is some connection here between them. So P is equal to force divided by area, and if I notice here, I have newtons per square meter, and this is called a Pascal, or PA. And very often we have kilopascals, or kPa, is equal to 1,000 pascals. And so very often what I'll have to do is divide the Pascal unit by this. And so now what we want to look at is what are the limits for this pressure, because I had this problem with the pool. Remember, we had the problem with the pool that the pressure wasn't the same everywhere. But can I define pressure at a certain level? Can I determine it at a certain level? The answer is yes, but we get to the limits that we had with macroscopic thermodynamics to enable us to do that. So if I look at P is equal to del Fn over del A, and I'm looking at that little volume that we had again, that del V prime. So I have my del V prime. And so what we're looking at here is we're looking at the force del F Z del F Y X. And this was this del V prime. So what we do, this del Fn is the average of these three. So what you do is you take the average of these three. And so what that enables with us in terms of the pool example, which is a big deal coming out of this for our practical use. So what this enables me to do is to say I can measure the pressure here, I have a P1 here, I have a P2 here, I have a P3 here, whatever. I have different pressures at different levels, and I can measure the pressure at those different levels. Now, what we talk about is how we're going to measure this. And so what I want to be able to do is to measure pressure as well.